Um, so this this work is due to myself, who do the underlying science and calculations, and Remy Kogon, who has been absolutely fantastic in constructing the interface for this. Now, this work has been funded by this Marie Curie grant, ERICA, which concludes at Surrey early next year. Remy was involved as a PhD student on that consortium grant, European grant, and started some of this interface work under that grant. Remy finished his PhD in, I think it was about May this year, anyway, about May this year, and has been working very hard on producing what you'll see later today. And we were going to place the software on GitHub. Unfortunately, GitHub doesn't accept such large files. Remy has produced a couple of standalone pieces of software that users will be able to install. This is a MATLAB-based software, but you don't need to have MATLAB to run these standalone versions. So we're thinking that that's going to be on Zenodo. I've set up the Zenodo site. I only have to hit publish, but obviously we just need to check that all that works okay. So there will be a link, I think, that we'll need to send around separately to this. I just want to start by a quick reminder as to what the two systems that this particular piece of software actually works with. So it is two variants of the 3-tau model that was explained last week, labeled HM and HH. And the schematic diagrams of these two systems are here as by way of a reminder. So the black is the solid, and our fluid has two environments. The surface environment, which is the deeper blue, is a single layer of, let's say, water. Its thickness is fixed at 0.27 nanometers. And so the fluid can either be in this slow-moving surface layer or the fast-moving bulk, which is the pale blue color there. There's various water molecules in each of these two diagrams. The leftmost diagram has paramagnetic ions distributed in the solid. They're the white crosses. This line at the bottom is in the model how we represent this distribution of paramagnetic ions. They are dispersed, but we represent them as a single layer of a particular density placed below the surface of the fluid by a distance 2 deltas, 2 times 0.27 nanometers. So the interactions that we consider for the systems with paramagnetics are these shown by the wiggly red lines. So the interaction between the paramagnetic and the mobile spins in the bulk fluid, and the interaction between the paramagnetics and the surface fluid. So there are 3 time constants in both of these examples: time constant associated with diffusion of the bulk, diffusion of the surface fluid, and desorption from the surface fluid into the bulk. For systems without paramagnetics, there's no paramagnetics in the solid, and these 3 sets of interactions are those that are considered within the 3-tau model: surface-surface, surface-bulk, and bulk-bulk interactions. Okay, so so that's just by way of a reminder of what that model is about. Okay. Just got stuck there. The software, here we go. The software works like this. The interface that we're going to see shortly is on the right-hand side. What the user, you provide, obviously, is the experimental data, the relaxation rates as a function of frequency. we have prepared a whole set of pre-calculated data sets. And these are read in by essentially a MATLAB script. But all you see is this interface on the right-hand side. Everything, all the working is at the back and behind all this. And as I said earlier, then we plan at the moment to put this software on Zenodo. I said I've set it up and I've just got to hit publish, but I think it will be useful to have the link to this video to put in the description in that before releasing it. I think that'd be helpful. Okay, right, let's quit that for now and let's go over to the interface, which hopefully you can see here. Okay, now this is the interface, and I wonder if it would be better just to share that interface. See if I can do that at this point because I've been with it for some time. Okay, I hope you can all just see the interface now. So this is what you would see. And I'm just going to give you a guided tour of what we have here. All I have done from the time it powers up is to import a data set. I do that through data import here. The data is, well, a couple of different styles of data set that are acceptable. This is a CSV file, a comma separated variable file that was read in. And it's of a sample of Q10 silica, very kindly provided by Jordan Ward Williams at Cambridge. So I'm very grateful to him for that. It's a good test data set to work with. This is not the very latest version, so I won't take you through these parameters and constraints up here, just to say that there's one changes some parameters, for example, the spin of paramagnetics, the frequency at which T1 over T2 is calculated, and so forth. And one can apply constraints as well through the buttons at the top of the interface there. So do stop me if you want to ask any questions. I should be able to see if anyone's wants to ask a question. I'll just start by just showing you what is on this interface. So obviously you can see the data. The interface reads in directly from Ceph files produced by Stellar's fast field cycling machines. And the ascending, descending for the experimental data is just whether the frequencies in the list in the CSV file are ascending or descending. What we see below that are three sliders. These are the three taus, the three time constants. And it's always good to activate these at the beginning. The first one is tau B. This is the bulk diffusion time constant. For pure water at room temperature, it's down here at about 5 picoseconds. I've never come across a fit in which the fit tau B is in excess of 40. So I tend to move the sliders so that it goes from, well, the lowest value it takes up to about 40 here. The second time constant, so we're selecting a range of values of time constant for the fit here. So this is tau L, the surface diffusion time constant. This is set at this lowest range, 10 to the 4 picoseconds. So normally this ranges from about, well, you can put it in this range, 10 to the 5, 10 to the 6, something like that would be okay for us. Now, tau D is the desorption time constant. Now, the desorption time constant and tau L, the surface diffusion time constant, these are linked because of the nature of the diffusion of surface fluid. So if it's moving around, it could either jump to a neighboring site or it could dissolve. So they're linked. So what we have here, again via a slider, is a range of values of tau d, desorption time constant, but that's linked to tau L. So the -1 here, which is where I normally keep it at, means that tau d ranges from 10 to the -1, 0.1 times tau L, up to, let's put it back to 1, back to 10 to the power 1, or 10 times tau L. So whatever tau L is, tau d can go from 0.1 times that value up to 10 times that value. A little bit further down, we have some constant offsets, and we'll come to those during the fitting process. So these are frequency independent contributions that one can add in. Now we come down to here to interactions type. Now the default is we're just having HH, which means we're assuming no paramagnetic ions in the solid. And what I do with a data set is look at the relaxation rates up the vertical scale here, the magnitudes of them. If they're low, which they are here, in this sort of region, then I'm thinking that certainly paramagnetic, the presence of paramagnetic ions isn't a huge influence. That's my first thing. Thought. So starting off with the HH model, no paramagnetics is a good place to start here. There are then two sets of data. We have the paramagnetic density we can ignore for the time being because we're just using the HH model, so that won't be used. But on the right, we have what we call the surface to volume ratio. This is the fraction of the water, let's say water in this case, that is at the surface. And it's difficult to know what value that might be, so I'm going to stick with the default here. There are three ways in which one can determine the quality of the fit. A linear least square method, which I tend to use if the range of relaxation rate isn't so huge as here. A logarithmic least square approach. So if one has data that spans, as sometimes does, from 10 to 1,000 seconds to the -1, I will tend to use the logarithmic least square approach because that de-emphasizes the large values at low frequencies. This data set has 31 points, data elements. The software allows one to remove the individual ones at the beginning or at the end of the list. So, for example, sometimes there's some very scatty data at the beginning of your data set. Well, you can remove those by, say, changing 1 to 2 or to 3 or something like that. And ditto at the high end frequency. We can't remove individual data in between. I'll keep that as it is. Here we have imposed values. 5 of these are set to 0, and these are 5 of the fit parameters. These are the 5 fit parameters, 3 taus, paramagnetic density if used, and X, the surface to volume ratio, which is over here. So if you want to specify a specific value for some reason, you enter that in those boxes, and the fit won't will override the sliders up here, for instance, if you enter a particular value of tau B. The surface density of water, which we have here, is the same as bulk water. So the default value is 66.6. Now, I don't know if you know or can picture water. There are 33.3 water molecules in a cubic nanometer of water, 33.3, and obviously there's 2 spins per water molecule. So a nanometer cube is like 3 by 3 by 3, roughly speaking, water molecules, if you want a picture of that. So, but this is the surface density. So one could vary the surface density of water in the model if one wished to do so, but I'll keep that as is. Okay, right, well, let's, as we have things set up here, let's just do a fit. We just press the do fit button and off she goes. So it's doing the background calculations. How long it takes to do the fits depends on the range of values being tested here. So I should say that as far as the X is concerned, the way these three boxes work is that the starting value as default here for X, the fraction of the water at the surface is 0.0008. And we're taking 50, we're trialing 50 values at increments of 1 times 10 to the minus 6. So it's useful to have a bit of mental arithmetic ability here. Multiply 1 times 10 to the minus 6 times 50. That's 5 times 10 to the minus 5, and you can see where that's taking you to. That's 0.0085. Okay, it's done a fit. It's not a very good one. So initially, we're trying to figure out what we need to change to get a better fit. It's done a good job at the higher frequency end of the dispersion curve. Poor job earlier on. The tactic is to look at the various parameters here, not terribly closely at this stage, but to see if any of them are out of range. So in other words, if we look at tau L here, that is 10 microseconds, which is 10 to the 7. And you'll see that that's my maximum value here. So it might be a useful tactic to increase that value, perhaps bring that up here somewhere and see if that improves the fit, because that's something that's out of range. Okay, so we'll let that chunter away at this stage. And eventually we'll find that the fit does improve, but not an awful lot. In the bottom left is the chi-squared fit parameter. So this is our linear least squares fit parameter. It was about 2,300 or something like that before. It's now down to 1,674. Still huge, still a relatively poor fit. So we look at some other parameter that we can change, and the key one here is X. Now, X is almost like a multiplier of the contribution due to the surface fluid. And if we look at X, this is also at its maximum value. The starting value we've set for X, the default is 0008. We multiply 1 times 10 to the minus 6 by 50, so it can't go higher than 0.0085. So let's change that over here. So we'll put it to 0001, something like that, and we'll just take some very coarse values of X because we don't know what they're going to be. So if, and I'll change this to 30 to quicken up the fit. So this will start at 0.001 and it will go in 30 increments of 0.0001. So it'll go from 001 to 004. And let's do that fit and see what we get now. Okay. And once we get something that's reasonable as a fit, we'll have a closer look at the output parameters, which are in the box over on the left-hand side here. Okay, so it's chuntering away. And a much, much better fit. Actually, a pretty good fit. And from about, what was it, 1600 as the chi-squared. This is now down at 10.8. So obviously a very dramatic improvement. So we'll now have a careful look at the various parameters that have come out here, and see to the extent to which they're meaningful. The first one is tau b. Now this is at 42, which is at the top end of the range, but I'm not going to worry about that too much at this stage. We can address that later on. Tau L is at 10 microseconds still, so that's here at 10 to the 7, so that's fine. And we note that the ratio tau D to tau L, I say it's round about 1, here it's 3. Physically, that's suggesting that water molecules at the surface of this silica makes about 3 jumps to neighboring sites on average before desorption. And physically, that's what that means. Now, we have here X, which is 0.0035, and we can see that that is in the range of our 0.001 to 0.004. So that's a fit value of X. And from that fraction of water at the surface, assuming planar pores as described last time, we can produce what we call a derived parameter. This H is the thickness of that pore if the system was constructed only of planar pores. And that's about 150 nanometers at this point. Now that's in general the least accurate quantity, and we'll discuss that again a bit later. N-para in the new version of the interface, that will be 0 in this case because there's no paramagnetic ions, and then that would be printed as a 0 rather than default values in this version. T1 over T2 is looking very large, 31, but we'll see that that will change shortly. Good chi-squared. But can we improve on that? Now, one thing I like to do in these systems is add in the intramolecular contribution, which is 0.182. So this intramolecular contribution is the contribution not taken into account by the 3 tau model, associated with the rotation of water molecules in the bulk. So that's 65% of the relaxation rate of water at room temperature. And that's something I like to just put in. We can just press do the fit just to see what change that makes. See if that 10.8 comes down with the addition of that. It won't make a particularly large change. So that's a frequency independent contribution associated with the rotation of the water molecule in the magnetic field. Okay, it's done, and well, the chi-squared has come down to 9.9. So in fact, that is a significant improvement at that point. So that's good. All right, but I'm not entirely happy with this. If we look carefully at the fit here, we can see that some of the points, particularly in the central region, are not well represented. This is a silica system. Now, our experience with cements, we know with cements, it's full of silica, calcium silicate hydrates and so forth, lots of silica in there. And it's the silica that tends to be replaced by occasional iron 3+ ions, and that's responsible very much for the relaxation response in cement materials. Well, this is silica also, but just silica. So there's the possibility that some of the silica here could be replaced by some iron 3+. So we can experiment by that through the software by adding in an HM contribution as well. So we can do both. So we can run the model with both HH and HM versions. In other words, because the relaxation rates are relatively low, we can explore whether both contribute to the dispersion curve. And if we just do that and just press the button, see how we go, and see how we can improve or not this fit this time round. Okay, so that's a nice feature. It's something one would use when it's not clear if one or other dominates the relaxation dispersion contribution.
I had one small question.
Yes, Alison.
For the intermolecular contribution, when you added that, it has off and on.
Thank you. I should put it on, shouldn't I? It worked.
Okay, I was just wondering.
I don't know. That's a good point, actually. It didn't make any difference, did it? It still worked. It did something different. Well spotted. Yeah. I hadn't noticed that. Remy, take notice of that. I think probably if I just put a number in here that isn't 0, it'll do it anyway, regardless of that switch.
Okay, I was just curious.
Yeah, no, thank you. Right, what have we got? Look at this. This is very dramatic. Our chi-squared has plummeted to 5.5. That's a big difference. That's a big improvement. And what you're seeing now in the figure are two curves. The green is the contribution to the relaxation rate associated with the interaction of paramagnetic ions in the solid with the fluid protons, and the red curve is the contribution associated with just the proton-proton interactions between the various fluid components. We notice immediately, actually, look at the value of tau B now. It's exactly where one would expect it to be. It's at 13 picoseconds. That's 2 to 3 times slower for the bulk fluid as compared to room temperature water, pure water. But of course, as per last week, we note that the second hydration layer of water is about 2 to 3 times slower in terms of its dynamics than pure bulk water, and that will certainly lengthen the tau B's that we would get compared to 5.3 picoseconds. We have now a different value of tau L. It's about 0.5 microseconds, and the ratio tau D to tau L is similar to what we had before. Okay, we need to check that these values of X and NP now are reasonable or within range. If we start with N para, I've just used the default here, you see. So this is 6.03 times 10 to the minus 4. So we have 0.00603 here, and that's actually 3 additions of 1 times 10 to the minus 6. So that is actually within the right range. So that's good. Out of interest, that corresponds to about a good factor of 50 less in terms of paramagnetic ion concentration here compared to what one would typically see in Portland cement based systems. It's a factor of 50 less if this is right. Okay. Now let's look at X, and X we see, now we've got a value of 0.13, But we're dealing with quite coarse values of X here. This is going up in quite coarse values. So I want to change that to the 0.0001. Let's make that more refined here. And that should take us up to 0.13 here. So 30 repetitions of this incrementation takes us up to 0.0013. And that's what we have over here. So that will help produce a better value, I think, of the fit parameter. And over here, what can I do with n para? I think I can change this to about 3, change this to something a bit coarser, perhaps, and have just perhaps about 30 of those and see what we get, and see if that makes a difference. Okay. So this one needs a little bit of mental arithmetic over here. I think sliders would probably be better, but there's such a large range of values that we can take here depending on the system. That's something that might be changed in the future. Okay. Just chuntering away. You notice that the H here, which is the planar pore equivalent thickness, is about 500 nanometers, whereas this is Q10 silica. So the Q10 silica means the 10 means 10 nanometers. So this kind of picture is of 10 nanometer channels. 10 nanometers for 3 tau model is as low as one can go in testing. So that may well be affecting the result here. But it depends very much on how the sample is prepared, and Jordan will know how it's prepared. If you've got powdered material, you'd have water between the granules and so forth. That will obviously contribute to the average value of the planar pore equivalent thickness of the water that one measures. Okay, so we have an improved chi-squared of about 5.2, which is really very good. And look, this is really a high-class fit that we have here. Tau B is about 20 now. We have tau D over tau L ratio of 3, which is what we expect, and tau L is about 7.5 microseconds. You know, tau L is moving around a little bit as we change these fits. So 7.5 is around about here in the slider. So that's all good. We notice we haven't looked at T1 over T2. It's high in these systems. It's consistently high, and it's settling down round at about 16, something like that, something very much in the teens. And again, if there was independent measurements of T1 over T2 ratio, this is calculated at 20 megahertz, then that will be useful as comparison. We tend to find, in fact, that T1 over T2 is pretty good in terms of matching up with independent data. The number of paramagnetic spins in the solid per nanometer cubed is not a parameter I would expect to be well reproduced. There's only 2 examples I have where an independent measurement of the paramagnetic ion density is known, and one of those is for a mortar, and the value we get from the best fit in the case of the mortar example is very close indeed to the measured value using electron spin resonance of the actual sample. And Remy tells me that for the mozzarella cheese example, where magnesium is the paramagnetic ion, again is a pretty good value, pretty good match between the fit and the value we get here. I think that's probably a little bit fortuitous. and I'll explain why just shortly when we go back to a slide. Okay, now there's one thing more I want to do. Okay, that one could stick at that, but from experience, there always is a sort of a relaxation rate offset associated with something or other. It might be just dioxygen, paramagnetic dioxygen in the sample. Here we have a little bit of iron in the silica, it would seem. And so what I would do is go through a process of changing the numbers here, adding a constant frequency dependent offset, seconds to the -1, and looking and seeing how the chi-squared changes. I've already done that, so I'm going to put 1.4 in here. I'm going to change some of these a little bit. So I'm going to make this 5. That's fine, that's fine, that's fine. And press fit. And I'm also at the same time going to save this output. So let's do this fit. This is the last one. And I say I have a notepad and I change this, this value of the offset and see what minimizes the fit. It's probably over egging the pudding a little bit, but there is a case here because of the apparent presence of iron in the solid that some of that iron goes into the liquid, and that would contribute an approximately in frequency independent relaxation rate offset. Yeah. Okay, so current chi-squared is 5.2. This is plummeted actually to just over 3. So that is a huge improvement as a fraction. Let's call this, what should we call this? 10 webinar as the output file. And that is an awesome fit that we have there. We notice that it's made some changes. Our tau B is now at 7.5. Tau L has gone up a fair amount. So, this is an important parameter to optimize. Again, the ratio is still around about 3, so that's rock steady. The number of paramagnetic ions in the solid, 6 × 10 to the -4 is tiny. As I said, it's about 50th of what one would see in a cement system. And the ratio has settled down about 18.5 here for T1 over T2. Now, this 1.4 seconds to the -1 as the offset, again, to give you an idea, if that's iron 3 plus aqueous, that corresponds to about 1/20th of 1 millimole of iron 3 plus, 1/20th of 1 millimole. So extremely small. Okay, that's the fit demonstration. I just want to talk about 1 or 2 other things, but are there any questions at this?
Hey, there's some on the chat.
Oh, is there?
Yeah. Right,
Stan. Oh, can we log scale? Well, the horizontal axis is log. The vertical axis, I don't think so. I'm not sure. I have to ask Remy that question.
No, it's not possible. But I already replied to Lionel.
You have you? Thank you.
Yes,
thank you.
No problem. Good job.
Yes. This is a good observation by Stan. Thank you. Yeah, you do have to be quite cautious about what conclusions one can draw from these numbers. You see some, like tau L, for instance, was changing quite a bit when we were making these adjustments to the parameters. Now, that depends very much on the nature of the data, actually. This is a sort of relatively smooth curve, and the tau L is trying to fix a sort of inflection point here. Much of the data sort of has a clear inflection point, and tau L is quite robust when one makes other changes. It's relatively well fixed, but not in this particular data set. Once one has a pretty reasonable fit, T1 over T2 is relatively not completely invariant, doesn't change too much. Okay, but yes, you're right, and that's something that one looks out for. If the data at the very low frequency end is quite scatty, it's good data here, but if it's scatty, then you find that tau D, for example, and hence the ratio tau D to tau L moves around a lot when you make fitting changes. So yeah, you have to look out for that, and it gives you an indication of how reliable some of these numbers are. Okay, so one would guess that tau L wasn't so well defined for this particular data set, because that's been moving around and changes as one changes some of these other parameters.
Dave, can I ask a question?
Yeah.
You've obviously got all the integrals stored in there in the background.
Yeah.
Are you linearly interpolating between the solutions, or are you taking just the nearest one? I'm just thinking that you could run into a hiccup where you have your starting value and your increment, and you make the increment so tiny, actually you just keep testing the same solution.
Yeah, no, that's right. The calculations are done for these time constants, different values of tau L, hence tau D and tau B, with 16 logarithmically spaced points in between. Okay, so it's those that are being explored. If one was to enter a tau L of one's choice here, then that would be linearly interpolated between those 16 logarithmically spaced data points per decade, I should say, per decade of tau L or tau D or tau B.
And a different question, I guess. You've got the intramolecular contribution there.
Yeah.
Can you fix all the parameters and switch the intra off to see what happens?
Yes. You mean fixed all the parameters here?
Yeah, if you typed all the numbers in there from the results, then presumably
Yes.
you could turn off intra and you could get the inter to intra contribution.
Yes, yes, and one can see how the fit changes. For instance, you could fix everything in here with the values that we've got, and then experiment by changing just tau L with everything else fixed, for instance. So in fact, Remy as a sort of separate sideline project has been doing something very much along those lines, in that we've been looking at how the ratio T1 to T2 ratio, how it changes when one of these parameters is changed, everything else kept fixed. Yeah. So one can keep, for instance, tau L, well, all the parameters fixed, and just vary tau L and see how T1 over T2 changes. So one can learn the dependence on particular physical quantities like that ratio change in a sort of a controlled manner. It's quite interesting.
So, and my last question is on that weighted linear in the least squares.
Yeah.
I'm just imagining you have a student who comes along and rather than taking log spaced frequencies, sets the machine, does linear frequency steps. And then potentially you have a problem because you totally overweight the tail, shall we say, of the distribution. Is that weighted linear designed to take that out? Is that something completely different?
The weights come from the Ceph data, I believe.
Oh, okay.
Yeah. So
it's nothing to do with the. You have to be a bit careful if you've got data which is not uniformly spaced in log space.
Yes. That's right. Yes, that's right. So the logarithmic least square method is as a means of, if these numbers are very high, of de-emphasizing low frequency.
I understand that. It's much more the spacing of the data points.
Yes. Okay, I'm going to do a new share and just go back to the PowerPoint. Okay, yes, the point I wanted to make about N para and or H, which is the planar pore equivalent thickness, which is determined from the surface to volume ratio. It's determined from the fraction of the fluid at the surfaces as per the fit. These, you have to take these with a pinch of salt. And there's just two examples here where you have to be very careful. In some systems, particularly with high concentrations of paramagnetic ions in the solid, there's clustering effects. So the paramagnetic ions cluster, and you don't get a linear relationship between relaxation rate and paramagnetic ion concentration because of this clustering. So one wouldn't expect to get a good value of the paramagnetic ion concentration in those systems. An interesting one that emerged from, again, some data from Jordan. Fantastic experiments. He's able to distinguish and separate out the dispersion curves of the alkyl protons versus the hydroxyl proton. And the magnitude of the rates are different. Of the two dispersion curves, the dispersion curve associated with a hydroxyl proton is larger in magnitude than that of the alkyl groups. And that would be reflected in the value of X and hence the value of H. Of course, the value of X is going to be the same, should be the same for both of these sets because it's the same material. It should have the same fraction of water at the surface, of methanol at the surface, regardless. But it's not. And the reason that is quite an obvious one once you've made aware of it. Of course, the OH is pointing towards the surface, so it's closer to the surface, and therefore the strength of the interaction is higher, and hence you get that higher magnitude. And it's because of the various assumptions in the built into the model. That's just something to be aware of. So one wouldn't get a reliable value of H of the fraction of fluid at the surface under those circumstances. And there's a whole host of other circumstances where caution is required. I've just quickly put up here some examples of this is just an HH protons only plot of a plaster paste which doesn't contain any paramagnetic ions. We discussed that a week ago. A nice set of data, and this is the more scatty data you see with large rates. This is of mortar, and a very significant relaxation rate offset secures the best fit here, and it's not a good fit. Well, it's a good fit considering the data. That's quite a significant concentration of Fe3+, which we know is in the pore fluid of such systems. That corresponds to round about a millimole per litre. And really just finally, I suppose, Remy's done all this magnificent work, and as per last week, again, I alerted everyone to the fact that we were putting forward a grant application to the Engineering and Physical Sciences Research Council UK to support Remy for 2 years to support you, the community, with getting going with this software, but also to extend, this is the important part, to these bio and nano model variants, the biological and sort of medical applications here. This is where the solid contains protons, and there's a whole host of examples where that might be useful, including not just in sort of looking at cartilage and other parts of the human body, but in suspensions of lipids and other types of suspensions and other sorts of liquids, that the model ought to be able to explore the behavior of dispersion curves in fast field cycling experiments of those systems too. We have successfully fit to a clay suspension, and there's absolutely no problem fitting there. The other extension is for the nano variant, and for the example you see in the Q10 silica, it's conceivable that a fraction, by nano we mean less than 10 nanometers, so it's right on the edge there, but certainly in, say, cement structures, where as the cement cures, then more of the water goes from the larger voids into nano spaces, typically 3 to 5 nanometers. So there becomes an increasingly significant contribution associated with the pore fluids in the narrow channels, the sub 10 nanometer channels. So I've got a list. Thank you for those of you who have already contacted me offering to provide a letter of support for this grant. I'm going to send out a draft copy of the application and a sort of a letter of support example to help with that. And I will also be contacting a whole host of other people in the hope of getting a little bit of support, which will be important in securing support for Remy to continue this work. Okay, thank you. Are there any more questions? Okay, there doesn't seem to be any more questions, and it's 5:02, so it's a remarkably good timing, I suppose. Thank you very much for coming along. Thank you very much for listening, and